Okay, finishing up section 8.1, this is page 4, last example. According to a Pew Research poll, 34% of adult Americans report that they are happy. A recent sample of 391 regular churchgoers revealed that 168 of them were happy. Comment on the requirements for finding a confidence interval for the true proportion of all regular churchgoers that are happy. Alright, so when we start thinking about the requirements, we want to think about what type of problem we're doing. This is a confidence interval for a proportion. And for a proportion problem, we're back to that idea of needing NP and NQ to be at least 10. And we've seen that the way we check that with proportion problems is to look at the number of successes and failures. In this problem, they looked at a sample size of 391. And they saw 168 successes there, 168 happy folks. So that's our x right there. So x is equal to 168, and that's greater than or equal to 10, so that takes care of part of our requirement. And then we also need at least 10 failures in our sample. And to look at that, we look at n minus x, and we have a sample of 391, so that's our n. So n minus x is 391 minus 168, and that would be 200 and something. Certainly it would be bigger than or equal to 10. So because both of those are at least 10, that implies that p hat is approximately normal. And if p hat is approximately normal, that implies that the requirements are met. So we're good to go on this one. Alright, so moving on to part B, obtain a 99% confidence interval for the true proportion of all regular churchgoers that are happy. So again, we're talking about a proportion problem. So our proportion problems have the formula for a confidence interval of p hat plus or minus a z star times the square root of p hat times q hat over n. So we want to assemble all these pieces and plug them in. I'm going to go ahead and start off with the z star portion of that. So I'll want to draw a picture representing this 99% confidence level. So draw our normal curve in and put 99% in the middle. That leaves 1% left over, but we'd split that in half among the two sides, so that would be 0.5% or 0.005 on each side. And then this is a z-score that we're looking for. So I'll find this one over here, this negative z. Negative z would be found by doing inverse normal of the area to the left, which would be 0.005. So let me go ahead and bring in the calculator for that. I want to use the distribution menu, inverse normal, and we have 0.005 as the area in our tail, so that gives us negative 2.576. And that's actually the negative z-score over here, so the positive one, which officially is our z-star, by symmetry would be 2.576. So I'm going to plug that in right there. And then there's some other stuff that we need to kind of gather as well. We need to know what our p hat is. And they don't give p hat, but they did say that we had 168 successes out of 391 tries. So p hat would be 168 over 391, and I'll just do that division off on the side. And I get 0.42. It's a 9.6, but needs to be rounded up, so that would be 9.7. So that's my p hat. And then q hat would just be 1 minus that. So q hat would be 1 minus p hat, which would be 0.5703. So now we have our p hat, we have our z star, and we know our sample size n was 391. So we have everything we need to plug into that formula, so I'm going to start working on that. So my p hat was 0.4297 plus or minus this z-score or z-star of 2.576 times the square root of my p hat, 0.4297, times 1 minus that, or Q hat, which would be 5703, and all of that is divided by my sample size, which was 391. Alright, and when we do this type of confidence interval, or any type of confidence interval really, we always want to show the answer to this plus or minus piece, and we'll see why as we go on to the next page. Let's go ahead and keep that work going. So this is 0.4297, and I want to figure out this plus or minus piece right here. So let me plug that into the calculator. So let's see, we have 2.576 times the square root. The calculator opens the parentheses, and I want to make sure I do not close that until after I have all three of those numbers entered in. So I've entered the p hat, the q hat, and the over n, and then I close the parentheses. And I always want to match the decimal places on the plus or minus piece with my point estimate, which is p hat here. This had 1, 2, 3, 4. So I'll put 0.064, and the next digit's a 4, but followed by an 8, so I'll round that up to a 5. And then finally I just do the plus or minus to get my confidence interval. So 4297 minus the 0.0645 gives me a left boundary of 0.3652. And I do that with the plus, and I get the right boundary, which is 0.4942. And then what were we doing a confidence interval for in the first place? We were trying to find a confidence interval for the true proportion, and the symbol for the true proportion, or the population proportion, is p. So I'm going to say that I'm 99% confident that p is an element of this interval that goes from 0.3652 to 0.4942. Okay, continuing on with our problem about the happy churchgoers, let's look at part C. So based on this interval, can we be 99% confident that the true proportion of churchgoers that are happy is higher than the 34% found for Americans in general that are happy? And explain. So on the beginning of the previous problem, they said that the study had found that 34% of all Americans were happy. The interval we just found is just for the churchgoers. Let's bring that back in for a moment. So there's that interval, and just talking it through, and then I'll write it out. If the proportion of churchgoers that are happy is somewhere in this range, then it could be as low as 36.5%, or as high as 49.5%, or anywhere in between. But if you're in between 36.5 and 49.5, then you're higher than 34%. So it does look like we can say yes to that. So I'm going to say if P is an element of that interval that we found on the last part, 0.3652 to 0.4942, then that implies that P is greater than 0.34. And that's the 34% number right there. So if P is anywhere in that range, then that implies P is greater than 0.34. So can I be confident in that? I'm going to say yes. So a confidence interval should be considered a list of all of the reasonable possibilities for the population proportion. I said the word if here because I don't know for certain that P is in this interval, but I'm confident that it's in there. These are the things that are reasonable possibilities for P, and all of those reasonable possibilities provide a yes. So when our entire interval is a yes to the question, that's when we can say yes based on that interval. Alright, let's go ahead and continue on. So is it likely that the point estimate in this problem is exactly correct? This is a question that we've seen over and over again. Is it likely? I'm going to take that to be a probability question. And the point estimate, that is the value from our sample, so that was p hat. And is that exactly correct would be meaning when we use it as an estimate, is it exactly equal to the population proportion? So I would translate their question as what's the probability that p hat is exactly equal to p, and we've said over and over again in chapter 7 that there was basically no chance of that. So since the chance is 0, is it likely? I'd have to say no. So the interesting thing about that is we're doing these confidence intervals, but we have to keep in mind that when you think about just the point estimate by itself, there's basically no chance you have the right answer. When we go to the interval, then we think that we do have the right answer. So how are we going from no chance of having the right answer to being 99% confident that we have the right answer? And the explanation for that is when we do it this way, we've given ourselves some room for error. So when they say how close do we think p hat is to p, what I'm always going to answer for that is the plus or minus piece from my interval. This was my p hat or my point estimate that I have no faith in that being correct. But once I added and subtracted 0.0645 to that to create this interval, now all of a sudden I was 99% confident that I had the right answer. So in order for that to make sense, I must have felt that the truth was within this distance of my estimate, because I didn't think the estimate was right, but when I went this far in each direction, then I was very confident I had it. So when we get to ask this question, how close do we think p hat is to p, we would give that plus or minus portion of our calculation, which is one of the reasons why it was good that we showed that in our work. So how close do we think p hat is to p? I would say that I think it's within 0.0645, and then I should put units on that. Well, I guess that's just a proportion. I could say within 0.0645, or I could say within 6.45%. So you could say that we gave an estimate that 42.97% of the churchgoers were happy, but we might be off by 6.45% with that point estimate. But once we give ourselves that room for error, all of a sudden we're 99% confident that we've got it. So because this is the room we give ourselves for error, we give that a special name. That's called the margin of error, something you've probably heard of before. When you see the news on political polls and opinion polls, they often state the margin of error. So that's the value that we add and subtract from the point estimate to create our confidence interval. That's called the margin of error. And just again, that summary of the logic, we know that p hat does not equal p, so we must give ourselves some margin for error, and in this section the margin of error is given by the formula below. Margin of error, we'll use a capital E for that, is z star times the square root of p hat q hat over n. And if you think about the formula that we use, that makes sense, because we're saying that the margin of error is the part we add and subtract. And if you go back and look at the original formula, we have p hat, and then we add and subtract z star times the square root of p hat q hat over n. So this piece right here is our addition subtraction piece, and so it makes sense that that would be our margin of error as well. All right, that wraps up section 8.1.